All right, well, hello y'all. So here's our last new lesson of chapter 9. We're going to do more log solving. We're going to see more extraneous solutions. And we might also see the whole change of base situation. Now take a look at this warm-up here. So I want you to figure out if this is true or false. So first, if log 2 of x quantity cubed, that's what this is. This is a quantity cubed. Quantity cubed. If the way to write that is this is sort of how to write it. So just notice where the cube is. Whoop, it's right there. That means the log is cubed. The x part of the log. So, anyways, if these two things mean the same, does log base 2 of x cubed equal log base 2 cubed of x? So think about it. Do, 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 do. All right, that's enough. The answer is actually false. These are not the same, and here's why. This 3 that is on the x can actually be brought out front using that log property. So then it would be 3 multiplied by log base 2 of x, and that is not the same as a log being cubed. So this is false. All right, so let's get to some solving here. You are probably going to really like these solving problems because they're really straightforward. So what we're going to start with is solving when it is a log equaling a log. So the first thing you want to look for, step 1 here, is that they must be the same logs. And they also cannot have any coefficients. So like, in front here, that there can't be any coefficients. Essentially, if we have the same log on both sides, no coefficients, then we can really just set the arguments equal. So this piece and this piece are equal. So 3x plus 1 is equal to x minus 5. So these are really simple. Now we solve for x. And I'm going to get 2x equals negative 6. So x equals negative 3. All right, so there's my x value. But I still need to check extraneous solutions. So let's go back to the log equation and plug this in. So we need to make sure that it works. Well, if we plug it in here, we're going to get 3 times negative 3 plus 1. And that's going to give us a negative argument, and that's not allowed. Same thing would happen here. If we plug in a negative 3 here, we're going to get natural log of negative 8, and that is no bueno. So it is extraneous. Remember the rules about a log. You always have to keep it positive in the argument. So this problem actually has no real solution. No real solution. And if you're super curious, you could try graphing both of these things in your calculator and see if they ever intersect. They won't, because there's no real place where they ever equal each other. All right, so then what about something like this? So this is, a log equaling a log. And the problem is we've got a 2 out in front of this one, but there is no 2 here. So we can't just set the arguments equal. But if I take this 2 and I apply it to the x, this now looks like of x squared equals log base 3 of x plus 2. Now I've got the same 2 logs equal to each other. So what I can do is set the 2 arguments equal to each other. So x squared can equal x plus 2. And this looks like something I might need to factor. So x minus 2 is equal to 0. Looks like I can factor this and get, what, x minus 2, x plus 1. All right, so I'm going to get an x value of 2, but I'm also going to get an x value of negative 1. And so there they are. But let's go check them. So I'm going to maybe go back to this version, but I could also go all the way back to this version. It doesn't really matter. Usually I say plug it into the very original, so I guess it would make sense to plug it into the original one. And when we do that, let's see. Here, the 2 going into that position is okay. Going into this position, the negative 1 is okay. And going into this position, the 2 is okay, but the negative 1 is not. So what we know now is that x equals negative 1 is extraneous. So that's an extraneous solution. So our only solution is the other one. So x equals 2. So that is your final answer for this problem. And then you're also going to see these exponential problems again. And, you know, it could be that you just end up using logs to solve them. Sometimes you can solve these just by changing, you know, the base numbers. We saw those like in 9F or 9G. But most of the time, these are going to require logs. So first off, the first step here is to go ahead and isolate the base and the exponent. That means that these are the pieces that can't really be separated from each other until you use a log. So I need to move all those other numbers kind of out of the way. So I'm going to do that, and then we get 3 e to the 2x equals 2, and then go ahead and divide by 3. All right, so e to the 2x is equal to 2/3. Now, this is a problem where my desired quantity, which is the x, is in the exponent. So I need to log it out. So log out the x. So I need to rewrite this as a log. So let's look at our 3 parts. Boom, boom, boom. And just rewrite it as a log. So this would be natural log of something. A log is an exponent, so I know that the exponent goes right here, and then the 2/3 goes right here. And so now this is something where I can turn to my calculator to help me evaluate. I will end up dividing by a 2. So natural log of 2/3 divided by 2. Let's see here. Natural log of 2/3, end the parentheses, and now divided by 2. And I'm going to get negative 0.203. Negative 0.203. So negative 203 is equal to x. All right. So there it is. Now, for this one, I don't really have to worry about extraneous solutions because look at where the x was. The x is an exponent, so the domain is infinity to infinity. So the x value, I don't have to worry about extraneous solutions for this. But when the x is inside of a log, that's a different story. So we're done with that. Let's try another one. So this is also an exponential equation because look at where the variable x is, right? It's in the x. Have to log it out. But our first step, we do need to do some isolating. All right, these are the pieces in that green box. Those are the pieces I can only separate them from each other by writing it as a log. But let's go ahead and get rid of that 3. So now I've got a 5 to the x minus 4 is equal to 6. And now I need to log it out. So I've got one piece, I got another piece, I got another piece. So this is going to be log base 5 of something equals something. The x minus 4 will go here, and the 6 will go here. And ultimately, I'm going to end up turning to my calculator here to get my final answer. Let's see here. This is log base 5 of 6, and then plus 4 is outside of the log. That's what my x value is going to be. So let's go to our calculators. You might have to remember kind of where some of these buttons are, so I'll show you. We are doing log base 5 of 6. So if you go to the math button, and you kind of have to scroll down a bit. Let's see here. We're looking for something that says log base. And some of the older calculators might not have this. So if you have an older calculator, your only way to solve this is to use the change of base formula. So I can go over that in just a second. With our newer calculators, this is what we can do. Log base 5 of 6. And then I want to hop out of the parentheses and subtract 4. And I'm going to get negative 2.89. All right, so negative 2.89 is equal to x, and we are done. All right, so for those of you that do not have that log button, what you would have to do here is you would have to do natural log of 6 divided by natural log of 5. That's the change of base formula. And then you would add 4. Oh, uh-oh. I think on that previous problem, I might have subtracted 4. Let me go back to the calculator here. Oh, I did. Okay, let's fix that. Plus. Okay. New answer, 5.11. All right. There we go. 5.11 is x. All right, now back to the pink. Okay, so if you are in need of an alternative way to solve this, you would use the change of base. So let's do that in the calculator so you can see that you get the same result. So natural log of 6, and your parenthesis, divided by natural log of 5, end your parenthesis, and then add 4. And there we go. 5.11. Yes. You should high five yourself, because I am. There it is. Okay, it worked. So this was also 5.11. It doesn't really matter which way you do it. Just make sure you know that change of base formula if that's kind of your only option. Okay, so then now that you have all the tools for solving, we can go one step further and give you some word problems. So the population of a city is given by this equation. Notice it is exponential growth. It is base E. Continuous growth. Where T is the number of years since 1990, according to the model, in what year will the population reach 250,000? Okay, so this seems to me like that is the value for P. So when I set up this equation, it's going to be 250,000 will equal 240,360 e to the power of 0.012 t. Okay, so now we're on a solving mission. Well, I would really like to reduce both sides. Let's reduce both sides by 240,360. 240,360. Okay, let's try that. So, 250,000 divided by 240,360 is going to give me 1.0401. 0401. So I've got 1.0401 is equal to e to the 0.012t. All right, so here we go. My desired variable is in the exponent, so I'm going to rewrite it. So I'm going to identify my three pieces and rewrite it as a log. So this would be a log base e, so this would be natural log of something equals something. A log is an exponent, so the 0.012t goes right here, and the 1.0401 goes right there. And now I'm going to have my answer here just as soon as I divide by the coefficient of t. So 0.012. All right, let's see if I can put this in my calculator. Okay, I'm going to do natural log. I'm going to hop up here and copy paste that number. Okay, so natural log of that divided by, notice I ended the parentheses on that, divided by 0.012. And I get let's just call that 3.28. All right, so what do we know? 3.28. 3.28 is equal to t. Okay, so that is in years. So it looks like in, about 3 1/3 years is when the population will reach 250,000. All right, so another type of question that could be asked is, what will the population be in the year 2050? So this is actually an easier problem. However, do remember that the problem is in terms of since 1990. So let's see here. 2050, take away your 1990. That's going to be what, 60 years have passed. So we need to plug in 60 for t. And so this problem is really more of just a plug and chug. We're going to solve for p. P is 240,360 multiplied by e to the power of 0.012 multiplied by 60. All right. So there you go. Let's see if I can remember all those numbers when I switch to calculator mode. 240,360. Okay. 240,360 e to the power of 0.012 times 60. All right. I think I did it. Let's see. Ooh, yeah. Okay. So our population in 2050 will be almost 500,000. So 493,803. 493,803. So 493,803. All right, folks. So that's what we're going to be doing with logs. I hope that was helpful, and make sure to bring the worksheet tomorrow so you can work on it in class. Adios.